In this video, we'll discuss tectonic plate boundaries and the map on page 5 of the Earth Science Reference Table. Before we get to the map, first you need to know what plate tectonics is, and it's the study of the movement, creation, the destruction of rigid lithospheric plates that lie above the underlying convecting mantle. So we have convection within the mantle, specifically within the asthenosphere, that's driving motion of all of these tectonic plates. And so here is the diagram on page 5, the tectonic plates map. First thing to point out about this map is that there are coordinates. So we have latitudes that go horizontally, as well as longitudes that go vertically up and down the map page. And so we can precisely locate positions using latitude and longitude. The next thing to point out is what is on the map itself. All right, so we see the North American plate, South American plate, African plate, Eurasian plate, and all of the other plates that you can see. We also see kind of the boundaries in between various plates. South American plate is here, African plate's there. This is a boundary between it. That boundary is known as the Mid-Atlantic Ridge. And we see these arrows pointing away from each other. So what does this mean? Well, luckily we have a key down at the very bottom of the map. The arrows just show us relative plate motion, so what direction is each plate moving. In the case of the Mid-Atlantic Ridge, they're moving apart. That is a divergent plate boundary, where we have two plates sliding past one another. That's a transform plate boundary. So the first type of boundary we're going to take a quick look at is, in fact, the transform boundary. So we'll take a look at the San Andreas Fault System. So in California, the west coast of the United States, that is a transform plate boundary. So what does this look like? So we're going to take a look at a cross-sectional view of a transform plate boundary. And this is what it would look like. We have one plate moving kind of towards us, one plate moving away from us, and they're just sliding past one another. And at this type of boundary, we have shallow to intermediate depth earthquakes, but no volcanism. So there's no sort of melting material. So we don't have any surface expression of volcanoes, only earthquakes. The next type of plate boundary we'll take a look at is the divergent plate boundaries. So an example is the Southeast Indian Ridge. Another example would be the Mid-Atlantic Ridge. Anywhere where you see the arrows pointing in opposite directions of each other. And again, this is a divergent plate boundary. So here we see a divergent plate boundary in cross-sectional view. We see the mantle convection, uprising material, so we call this upwelling of hot mantle material, causing melting near the surface, which results in an extensive volcanism. And this volcanism actually creates new crust. Right, so this is where oceanic crust gets created at these locations known as ridges. Right, and the other thing to notice here is that the plates are actually separating. They're moving in two separate directions. So we can see plate on the right side is moving towards the right, plate on the left is moving towards the left, strongly influenced by the convective cell underneath the lithospheric plate. Because we have plates splitting apart, we also see a lot of shallow earthquakes, especially around the ridge. This is where new crust gets created. So that uprising mantle material causes melting within the rigid mantle. That melting material will rise because it's less dense, because it's hot, and that's what we see as the mid-ocean ridges. So this is where brand new crust is being created, and it gets pushed off to either side here. Another aspect of the crust that we can see here is that the oceanic crust is much thinner than the continental crust. And that's something that is always going to be true. Not only is it thinner, it's also more dense, because the oceanic crust is basaltic, continental crust is granitic. There's an age relationship that exists within oceanic rocks. The youngest rocks are going to be found near the mid-ocean ridges where they're created. That shouldn't be surprising. And they get older as you move away from the ridge. So the farther you find yourself from a mid-ocean ridge, the older the oceanic rocks will be there. Now, the older the rocks become, the more dense they become, because they're going to cool off and become more dense as they move away from the ridge and the heat source. One of the most important pieces of evidence supporting the theory of plate tectonics is the presence of paleomagnetic data within the oceanic crust. When oceanic rocks crystallize, they cool, they'll actually trap the magnetic signature under which they formed. And so the magnetic minerals within these basaltic rocks will align themselves with the Earth's magnetic field, and they represent the field under which they formed. So rocks A and F are the oldest. They formed at the same time, so they have the same magnetic polarity. They formed under conditions known as normal polarity. That just means they formed under a magnetic field that's pointing in the same direction as it is today. Rocks B and E formed under a reverse field. The youngest rocks in the diagram, C and D, formed under a normal field. Right, so we see these back and forth magnetic reversals as an indicator of seafloor spreading. We're going to take a look at the remaining type of plate boundary. And a good example is the Aleutian Trench. And of course, this is a convergent plate boundary. Notice here the arrows are pointing together. So at convergent boundaries, plates are colliding with one another. So in this example, we see two oceanic plates colliding, denoted by the arrows facing each other. And this is actually known as a subduction zone. So this word subduction indicates that one plate sinks or dives kind of beneath another plate. Right, so we have shallow to very deep earthquakes within subduction zones. Some other features we always have in subduction zones are a trench, and we're going to end up with a volcanic arc or a volcanic island arc. If the overriding plate is an oceanic plate, you will end up with a volcanic island arc. So that's an island chain created from these volcanoes associated with the subduction, or the overriding plate can be continental plate, in which you will also have a volcanic arc. It will just be on land. So here we're going to take a look at a practice problem. Again, feel free to pause the video and try this out for yourself. I'll be implementing the CUB strategy, where we're boxing what we're looking for and underlining key information or what we know from the question. So we're looking for which boundary is most similar to the plate boundary found at the Mid-Atlantic Ridge. All right, so we know we're looking for something similar to the Mid-Atlantic Ridge. So we go to the map on page 5. First, we need to find where the Mid-Atlantic Ridge is. And there we go. So what kind of plate boundary is this? Well, we'll check the key. It's a divergent plate boundary. So we're looking for another plate boundary that happens to be divergent. Answer choice number 1 was between the Eurasian and Indian Australian plates. So the Eurasian plate is right here. Indian Australian plate, the boundary between it, we have two arrows pointing towards one another. This is not a divergent situation. This is convergent. They're colliding with one another. So choice 1 is not correct. Choice 2, we have the Cocos plate and the Caribbean plate. Again, we take a look at the pattern, and we see this kind of sawtooth pattern. That again is convergence. So those plates are colliding with one another. The third example is the Pacific and the Nazca plate. So we take a look. Here's the Pacific plate, the Nazca plate, and lo and behold, these are actually separating. They're diverging, which is exactly what we're looking for. So we take another look at the problem, and we've already determined that number 3, the Pacific and Nazca plate boundary, is in fact the divergent boundary. All of the other 3 are convergent boundaries. It's practice problem number 2. Again, I'll be implementing the CUB strategy. Feel free to pause the video here and try this out for yourself. So we're looking for a cross-section that best shows the convection occurring. And what do we know? We know it's beneath line XY. So this line XY, we know that we're looking again at the Mid-Atlantic Ridge. Right? So in the last example, we determined that the Mid-Atlantic Ridge is a divergent boundary. So the plates need to be separating. They need to be going in opposite directions or spreading apart. So we have to ask ourselves, in which one of these situations are the plates actually separating? So if we just finish off the convection cell here, cell on the right, the arrow coming back is pointing towards the center. Cell on the left side is also pointing towards the center. This would represent a convergent boundary, so it's not number 1. Number 2, we have arrows rising up and spreading. Right? So this is, in fact, a divergent boundary. So the correct answer here is number 2. Number 3 makes absolutely no sense whatsoever. It's not how convection works. And number 4 would show a convergent boundary, just not showing any kind of continuation of the convection cell at any sort of depth. Right? And the last practice problem we'll take a look at here, and this gets into the paleomagnetic signatures that were mentioned before at mid-ocean ridges. Again, we see the Mid-Atlantic Ridge. This is probably the most popular boundary that gets talked about with the Earth Science Regents, probably because it's so close to New York State. It's the closest boundary to us. So again, we're looking for which cross-section best represents the magnetic field pattern. And so what do we know? Well, we know what the pattern is on the east side of the ridge. And we know that the kind of white dotted pattern means that it's reverse polarity, and the gray pattern means it's normal polarity. So first thing we need to realize is that rocks right here will match rocks that are created right here. So we need to start at 0 with a normal polarity, followed by a short period of a reverse polarity, normal polarity, reverse polarity. This is just going to be a mirror image. So imagine taking this whole section and flipping it across the ridge. So if we take a look at our answer choices, we can very clearly tell that 2 are wrong. If we look at option B and option D, both options show us at the ridge the rocks are reverse polarity. We know that the rocks right near the ridge should be normal polarity. So we can immediately dismiss options B and D. So between A and C, we have to see which one is kind of a mirror image of what's on the east side of the Mid-Atlantic Ridge. So we start at the ridge and we work our way towards the left, towards 80 million years old. Just before 40 million years old, we have a pretty long section of normal polarity, which is demonstrated in option A, but not demonstrated in option C. So option A is the correct answer here. This is just a perfect mirror image of what you see on the right-hand side. I hope this video was helpful. If you have any comments or suggestions, please leave them in the comments below.